So I actually lied. This is the second to last video. So the book has some commentary between Corollary 440 and Definition 441, which I'm going to skip over real quick and then come back to after the definition because it uses the two words that are defined in Definition 441 in the description of in the commentary on finite dimensional Hilbert spaces. So we begin Definition 441. If T is an operator in a Hilbert space H and M is a closed subspace of H, then M is invariant subspace for T if T maps M into itself. And an invariant subspace M for T is called a reducing subspace for T if you also get that it maps the orthogonal complement of M into the orthogonal complement of M. Now, the book's discussion about finite dimensional Hilbert spaces brings up the fact that if you have both the reducing subspaces and the invariant subspaces have a nice structural property related to the eigenvectors of a matrix or a operator in a finite dimensional Hilbert space. So if I have some operator T that is normal in a finite dimensional Hilbert space, then one of the eigenvalues for the matrix, if you take its eigenvectors, their span is a reducing subspace for T. As well, it has a property where it can be used to put T into its diagonal form. Now, if you restrict the requirement of normality on T, then you obviously lose that ability to put it into diagonal form. However, the span of those vectors, of all of the eigenvectors, is still an invariant subspace under T. Now, the reason that the book brings up this commentary on finite dimensional Hilbert spaces is that there are not an analog to these structural properties of the invariant and reducing subspaces when you're in an infinite dimensional Hilbert space. However, they're bringing it up, so there are still a lot of applications, and the definitions in the finite dimensional cases are equivalent to the ones in the infinite dimensional cases. So everything works nicely, but we do lose the properties when we go into infinite dimensions.